So here's what we had last time. We had shifts and reduces on configurations, right? Let's just take a quick look through here, and there's the algorithm. Oops. And how to fill in the table. There we go. So we've done all that stuff. That's good. That's good. We've done that. Close operation. We've done the go to operation. We've done all this stuff. That. Right. So I know what we're going to do today. We're going to do 410-2. So remember when we did the LL parsing, we said, we create this table and we fill it in by using first and follow sets. And if we ever get any entry in the in that M parsing table that has more than one entry, then the grammar is not LL1. Now we could run into something similar here, couldn't we? Because what if we have, I don't know, we'll pick a row. So dot 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 dot, and I don't know, put an X there, and we'll put an A here, right? So this entry here is action A comma X. Now, what if that were equal to shift, I don't know, Y? So let me just draw it as a little box. So that's that now. Actually, can I just make a few changes here? I think I want to call that A, and I'm going to call that S for state. So in state that, and I see an A reduced by, and then maybe I can just make this box a little bigger, reduced by A goes to alpha. So what if I got that? Then what I have here is a shift reduce. Oh, actually, it's a possible. No, that is a shift reduce. Now, how could that happen? How could I end up getting two different things in here? Obviously, I can't get a shift, right? Because if I think about it, how do I get two things in there? Well, let's see. We can do the corresponding. So what would the graph look like if I had something like that? Well, I would have to have a state somewhere, and that's state S, so item set IS, and that needs to point to somewhere that is state Y, and it has to have an A here. Then in here, there's got to be something that has a dot in front of the A, because I'm shifting on that. And then since I'm reducing by A goes to alpha, that has to be complete. And little a has to be in the follow set of capital A. Now, why do I say that? Well, because if you remember back, look at this guy here. Why did we not get an error in this state, right? Because here, surely I have a dot in front of a terminal. So, and I have a completed item here. So if that plus is in the follow set of C, then I would get a reduction error. But I think follow set of C is just $1, right? Because if I'd had a plus here, then in state 1, I would have had to put R5 here, and I would have got a shift and a reduce. So whatever I'm shifting on must be in the follow set, and if that's the case, then I end up with something like that. Right. What about a reduce conflict now? So maybe I can just be a little sneaky and just grab part of this. There. And well, that stuff is still true. Now, if I have a reduce conflict, then we have something like this: as reduce by, I don't know, A goes to alpha, and reduce by B goes to alpha. Now, how could that then happen? Well, again, we can consider sort of the corresponding graph. So let's say that this is IS, and I have A goes to alpha dot, like that, and B goes to alpha dot, like that. And little a is in the follow of A, and little a is in the follow of B. So if that's the case, then of course I get a reduction by both of them. Let me ask the following question that just occurred to me. Is it possible to get A goes to alpha dot, B goes to beta dot, where alpha is not equal to beta? What do you think? So do I have to have the same right-hand sides on the two productions that I'm reducing by? It's sort of a hard question, but in theory you should be able to answer it, because you only have to remember one thing, which is this original algorithm that we started out with. Well, if I can find it. No, it's the very first one we did, where we said, for as long as the handle is not on top of the stack, push things onto the stack. And then we sort of waved our hands and said, right, at some point the stack is going to have the handle on top, or the handle is going to be on top of the stack. So if I have a reduction state, if I have a complete item in a state in my SLR graph, then that's because the handle is on top of the stack, right? There's only ever one handle, which is the one that if you use it, it will bring you closer to the start symbol in a reverse rightmost derivation. So is it possible to have a state that says, right, you can either choose to reduce by a goes to alpha, or you can choose to reduce by b goes to beta, but alpha is not equal to beta? And the answer, of course, is no, because there is just one handle. And if we get to a state that looks like this, that sort of suggests that there are two possible handles that can be on top of the stack. But if there were two possible handles, then that doesn't make any sense, because if I had the alpha, I would reduce by that one, and if I had the beta, I would reduce by that one. But this situation says I have both of them, and I can only ever have both of them at the same time if they're equal. So that's why I picked the same there, right? So we can get reduce conflicts if I have more than one completed item. I suppose you could actually, that's not entirely true what I'm saying here. So I suppose or one or more are epsilon, because that could happen, right? You could certainly always have some epsilon transitions. So in general, if I have a if I have a state in my SLR graph that looks like this, A1 goes to alpha 1, A1, beta 1, dot, 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 AN goes to alpha N dot ANBN. So we have a whole bunch of items that we can shift on. And then we have this. Now, there's sort of a difference in when we talk about a set of items that we've just sort of made up, and the set of items that can appear in states of an SLR parser, right, in the graph, because those graphs, the state sets there, are created using specific rules, so we can't just be sort of willy-nilly anything. So for example, if we had something like this, the same thing applies, that these gammas, these guys here, would either be the same or some of them would be epsilon. So if we have something like that, then we can say when do I have a shift-reduce conflict? Well, I have a shift-reduce conflict if I can shift on something and reduce on it at the same time. So basically, if any AI is in the follow of any B sub j for any j. So if there is an AI that I can shift on that also is in the follow set of any of the B's that I reduce by, then we have a shift-reduce conflict. Well, when do we have a reduce conflict? Well, we would have a reduce conflict if I have two follow sets of these B's that have the same. So if there exists I and j where I is not equal to j, such that the follow of bi intersected with the follow of b sub j, and that is not empty. Right. So I think that's what I want to say about first, shift reduce and reduce conflicts. I do want to say just a little bit about kernel items. Now, before I do that, if I flip back to, if I can find the graph here, do I have it in a nice large version? Yeah, this one, for example. This one's good. I look at this one, and I don't know. Let's pick this state down here. And if I asked you, what is the smallest subset of these three items that I could have, such that if I applied the closure operation, I would get the entire state back? So clearly it has to have at least one thing in it. So is it possible to recreate this entire state by applying the closure operation to a subset of these? And the answer is yes, because that's how it was created in the first place, right? Remember what the go-to operation does. So when I have an F here, and we want to do this go to I5 on the F is defined as find everything in here with a dot in front of an F, move it in there, and move the dot one over, and then apply the closure operation. So we can see every time I apply the closure operation, the dot is all the way to the left. So by just looking at this, we can see that these two, these two, these two, and these two were all added to these sets based on the closure operation. So it's almost correct to say that any item where the dot is all the way to the left was added by the closure operation, and therefore is not a kernel item. Because the kernel items are those generating items that are needed in order to regenerate the state. Now, somebody might say, well, wait a minute, what about this guy here? Well, this one is special, because if I threw this one out, then I wouldn't be able to generate I0. So the kernel items are all the generating items for this graph. So that one, that one, that one, that one, that one, that one, and that one. Because that's all I need in order to be able to regenerate the entire graph by applying the closure operation again. Because those two came from the fact that there's an F there. These two came from the fact that there's a dot in front of a C there. These two came because there's a dot in front of an F here, and those two because there's a dot in front of a C there. So we can definitely say that for an item set I of items, I suppose item sets are of items, what else would they be? So for an item set I from a state in an SLR parser, kernel of I is J. J is minimal, such that if I apply the closure to J, I get I. That J is exactly those items that you dragged into new states. So when I look here, what did I drag from here to here? That one. What did I drag from here to here? That one. What about from here to here? This one. What about from there to there? That one. Similarly from here to there. That one. From here to here. That one. From there to there. That one. And we can say that any kernel item is of the form A goes to alpha dot beta, where alpha is not epsilon. So i.e. the dot is not all the way left, except for on the special start item, where it looks like S goes to something alpha, where S is the start symbol. That one has to be a kernel item, because if I didn't, then I would never get started, right? Right. Now, let's try something else. We know left recursion is bad for LL parsers. So let's just see how that goes if I do it for a with an SLR parser. So if I have S goes to A goes to A, and A goes to B, we'll call that rule 0, rule 1, and rule 2. Now, is that going to be a problem? I don't know. We can just try. So I0 is the closure of the set of the one item that looks like S goes to A. Alright, so S goes to dot A by closure, A goes to dot A, or A goes to B. So that was one of the examples where we did end up having everything in the start. Alright, let's see, we can transition over here on an A, and I get to I1, which is go to I0 on an A. And, well, let's see, I gotta take that one and that one, because a dot in front of an A and a dot in front of an A. So I get S goes to dot A, and A goes to A dot A. Oh, no, I don't. I need to move that dot, don't I? Uh-oh. There's a potential for a shift-reduce conflict. Is there a shift-reduce conflict in state I1 in this graph? I'm not frozen. I'm waiting for somebody to say something. Well, then you haven't committed, I suppose, if you're unsure. So what is required for a shift-reduce conflict to be in state I1? Well, it is that I can shift and reduce on the same. If I continue with this guy here, I know I'm going to have something that looks like this. So I2, and it says A goes to A dot, doesn't it? And real quick, this one over here says A goes to B dot. We'll call that I3. So that's the entire graph. So in order for me to have a shift-reduce conflict here, I got to be able to shift and reduce on the same look ahead. I can shift on that A. The question is, can I reduce on a little a? Well, I can if little a is in the follow set of S. So if little a is in the follow set of S, so we can say I1 has a shift reduce conflict if and only if A is in the follow of S. What is the follow of S? Where S is the start symbol that only appears once on the left-hand side. What can follow a correctly derived program on the input? End of file. Yeah. So therefore, no shift-reduce conflict, because A is not in that set. So looks decent. Can we do the graph, the table real quick? I think we probably can. It's not particularly hard. Let's see, what do we need? 1, 2, 3. We need some more stuff here. That's my go-to table. And I have A, B, dollar, and I have 0, 1, 2, 3. That's a B. In state 0 on an A, I go to 1. In state 1 on a B, I shift to 3. In state, oops, that's not 2. In state 3, state 0 on a B, I shift to 3. In state 1, I accept, and I can shift to 2 on A. And in state 2, I do a reduction by, well, what's the follow set of A here? That's just A and B, right? So this is just a reduction by rule 1, reduction by rule 1, and the other one is rule 2. So we get that, no shift-reduce conflicts because there are no multiply defined entries. Cool. So no problem there. Now what about right recursion? Because leftmost derivations in an LL parser have problems with left recursion. The rightmost in reverse does not have a problem with left recursion. Can we conclude that right recursion is going to be a problem here now? Well, I don't know. We can give it a go. Why don't we use the same grammar and just swap the recursion there and see what happens? Well, let's see. Here's I0. Its S goes to dot A. Then we apply the closure operation. We get that. We get that. So basically we got exactly what we did last time, everything. So now here I can leave on an A, and I get to, let's call that I1, and that's S goes to A dot. That's when we're going to be done. And I can leave on a little a. We'll come into I2, which is A goes to A dot A. Applying closure, A goes to dot A, and A goes to dot B. So I said once you've done a few of these closure things, it's super easy, right? And we can go down here on a B. So we call that I3. So that's A goes to B dot. Then we can see that we can cycle around here on an A, because if I do that A, I get this, which under the closure gives me just that. And I can go over here on a B, and I can transition out here on an A. We get to I4, which I have A goes to A dot. So we do that. Now, are there any shift reduce conflicts here? No, because the only place I reduce is here, and there's nothing to shift on. So the answer to that is resounding no. So right recursion is not a problem either. I think we just briefly talked about the dangling else problem. Did we even skip that last time? I think we're going to skip it again. But if you try to implement sort of the obvious if statement logic using a rightmost derivation in reverse, so using these SLR graphs, you're going to again end up in exactly the same problem. It just doesn't work because we get shift reduce conflicts. So that doesn't work either. Now, the last thing I want to talk about is LR1 parsing. And what's the point of LR1 parsing? Well, the easiest way to explain this, or to sort of argue for it. I really don't want to do example 433 because it is a little complex, and you can take a look at it yourself. I want to try to motivate it in a different way. And then once you understand that way, 433 probably makes more sense. So in SLR 1, we fill a row in the action table for a complete item using the follow set. For example, if Ix contains A goes to alpha dot, then the action table in state X on a little b is reduced by A goes to alpha for all b in the follow of A. That's very general and broad by simply saying, right, we're going to go look in the grammar and we're going to find everything that can possibly follow a capital A. And if we see that on the input, when I have that handle on top of the stack, we'll just reduce by it. And surely, if you think about that for a little while, that is very general and does not take context into account. So for example, if you look at a grammar, let's see if we can make one up. Let's say we have S goes to something, and I don't know, X goes to something, something, something. We have an A and a little a and some other stuff, and let's say we have a Y dot dot dot, A and a little b dot dot dot, and then we have A goes to, I don't know, X or Y. Now, if we have a derivation, now before we do that, just look at what I did here. I created a grammar that has A in a number of different places, 2 to be particular, and then I put different values here, and I made it simple by putting just terminals, because what's the follow of A? Well, it's that A union that B. So I just get AB. And once I just have that follow set, now I don't have any contextual information about whether or not I expect to see an A or if I expect to see a B. So if we have a derivation that looks like this, S goes to something in a number of steps that has an X in it, and we then take another step and we get to something that has that A in it, then whether that A becomes an X or a Y is really not all that important, right? Just at some point we might see an X for the A, and some points we might see the Y. But that doesn't matter. But if you think about the situation where if I put the dot here, so there's going to be some state in my graph in which I have the item X goes to dot dot dot, then I have a dot A dot dot dot. And in here, I'm going to have A goes to dot X, and A goes to dot Y. There could be other stuff as well, right? Then I'm going to have definitely something X here, and definitely something Y here. I should have just done one X. It would have been easier, but that's just okay. So I have A goes to X dot, and A goes to Y dot. If you look at this, both this one and this one, so let's say IJ and IK. So if I make row I, oh, actually, J and K, A and B. So in order to fill in this one, I need to say reduce by, oh, should we give them I will fit it in. So this says reduce by A goes to X for every element in the follow set. So I'm going to need to say reduce by A goes to alpha, reduced by A goes to alpha, and down here, reduced by A goes to, oh, sorry, not alpha, X, and this one by Y. So I would get something like that if I filled it in using the rules that I have. But let me ask you something. If I got to here from up there, what is going to be on the input when I want to do a reduction by that? Well, the follow set says it's going to be an X or a Y. Sorry, the follow set says that it's going to be an A or a B, right? So follow of A is either A or B. Is it possible that when I get to state IJ and IK, so when I get down here, that indeed the next thing on the input is a B? I mean, how could it be? Surely the only way to come down here and come down here is if the input looks like either X or Y, something, something, something. I would get here if it's X, and I would get here if it's Y. Fair enough. So what happens when I do the reduction down here? Remember, I'm going to jump back to the state where that dot was there and say, I've done an A. So that is one long. It must have come from up here. So at some point I'm going to come back up here, and I'm going to say I'm going to transition to another state. We'll call it IN, in which I have X goes to dot, 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 A dot A. What does that mean? Well, it means that whenever I do that reduction or that reduction, I'm going to end up over here. What does that dot in front of that A there mean? Well, it means that I can only progress if there's an A on the input, right? So what if down here I'd said, right, if there's a B on the input, I'm just going to do the reduction just like that says, and then I'm going to go back over here, and then I'm going to come in here, and now we're going to be in trouble because there is no B on the input. Sorry, there's no way to get out of this because this only works. I can only shift out of this guy on a little a. So if I have a b on the input when I'm trying to do these reductions, then we're never going to end up getting here. We're going to get in trouble when we get to here because there's no way to shift out of here on a b. So we could actually do the following and say, right, because of the context, because of this dot being here, and I know that I'm traveling this way, if I look at what comes after this a, I know for a fact that if I look at this and we call it, let's call that delta, then I know that the first of delta, and I'm going to take epsilon out, is a subset of the follow of a. Why is that? Well, because that's how the follow sets were computed in the first place. Over here, I looked at the first part of that, and I looked at the first part of that, and then I just unioned them together. So I know for a fact that what comes after this a here is indeed a subset of the follow set. And what I'm saying is, right, in this situation here, that first set is just going to be an a. I put that in so that it was easy, but it could certainly be some non-terminals that require you to do some more computation. But in this case, it's fairly simple because it's just an a. But what I'm saying is, well, maybe we should only reduce by a when I get down to here. So we could say, but only a on the input works. So we should cross those out. And then, of course, the question now becomes, how do I figure out what to reduce by when I come down here? Well, what you should reduce by is exactly first of delta minus epsilon. So we can say use first of delta minus epsilon instead of the follow set. So what we do is we say, right, every time I have the closure operation where these are added, I'm going to determine what that set is, and then I'm going to carry it with me as a second parameter here. So let's set that up, because all I have to do is just throw in a set of elements here. So let's define so an LR1 item, it looks like this. Something here, comma, something here. What goes here is an LR0. Actually, it's a rule with a dot on the right hand side. So just like an LR0 item. And what goes here is a terminal with which we reduce when that thing is complete. So for example, if I have a goes to alpha dot beta comma little x, then when we have a goes to alpha beta dot comma x, we reduce by x only. So that's exactly what we did here. We said, right, what's the first set of this? Well, that's just an a. So really what I would like this thing to look like is a goes to, oops, a goes to dot x comma little a, and I want that to look like a goes to dot I comma little a, and this one down here as a goes to x dot comma little a, and this one as a goes to y dot comma little a, because then I know what my reduction look ahead. We're going to call it a reduction look ahead. Many other books just call it a look ahead, which is completely confusing. So we'll call it a reduction look ahead instead. And that's what we reduce by rather than the follow set. And those reduction look aheads are only ever created, they're never changed. So they're created when I do the closure operation, but as the dot travels, it stays the same. Well, of course it stays the same because I need to transport it from where the dot is all the way to the left to where the dot is all the way to the right, with the information that I should only reduce if I see whatever's in that first set. So what we can do is we can say, if we have a goes to alpha dot beta comma x, and a goes to alpha dot beta comma y, then we represent that as a goes to alpha beta comma xy. That way we don't have to write so darn much. So it's just a little easier if we do that. This part is called the core, not to be confused with kernel. That is the reduction look ahead. And it is only ever used in states where the core is where the core of the item is complete. So it really is just a hang around on from the time that it gets created by the closure operation until we get to the very end. Right. So if I go back to this and I said, actually, so let's see if I can do. That's not what I wanted to do. I wanted to do that. I'm gonna grab this thing here. And we'll plunk it in there. I'm just going to make it a little smaller, and then I'm going to clean it up a bit. So we'll get rid of that, 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 this nonsense, and that. And that's the SLR. Now let's try an LR1. Right. So I have my I like that. I have X goes to something, 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 dot a little a, something, something, something. And then I have some sort of reduction look ahead here. I don't know what that is because we can't tell from the context, but there is one. And that reduction look ahead is used only when that dot has traveled all the way to there. So whenever we get to the state where that dot makes that a complete item. But what we do now is we're going to add a goes to dot x, and we're going to add x goes to dot y. And what we need now is, let me just close this state. We need something here, which is the first of delta minus epsilon, where this is delta. Well, that's easy enough. That's just A. You know what? When there's just one, then I'm just going to write it like this. Like that. Okay. That means that when I run out of space, when I get down to here, and I have A goes to X dot, then I have dragged with me my little a. And similarly for the y, a goes to y dot little a. There we go. And let me just move this to there, because I just want to put in the rest of this. So that one there was an a, it's still an a, and I get to a state that says x goes to dot 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 a dot little a dot 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 comma, and this of course is the same, because doing the go to operation, or the first part of the go to operation, doesn't change look aheads. It's only the items that are added by the closure operation that get, well, of course they get a new look ahead, because what would they be if they didn't get a new one? And then of course again, when I transition on an a here, and I get to x goes to dot 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 a dot 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 dot, that is still the same, because the dot is just traveling. So that is also the same as that. So what we can see is, we can, if I put in my brackets, we can simply compute these new reduction look-aheads very easily by just looking at this situation. I have a dot in front of an A. Because A causes these to be added by the closure operation, then I pretend, hey, what's going to be on the input when I move that dot over here, which I can do once I've done either of those reductions, right? Because if I've seen an X and I end up coming down here, doing that reduction, going back to that state saying you've done an A, that plunges me down here, dots on the other side. Similarly with the Y there. So by looking at this thing, what can appear after that A here? Well, that should be the stuff that I would do reductions on if I see that on the input. So we can redefine closure 0 to closure 1. And that 0 is 0 reduction look ahead. Use the entire follow set of the left hand side. Closure 1 is use your reduction look ahead. So that's definition 417. So again, we can say if I is an item set of LR1 items, then closure 1 of I is the minimal set J, where the following rule can no longer be applied. And what is that rule? Well, it's the closure rule if A goes to alpha dot B beta. And now we got to have a reduction look ahead. So if that's in J, then do the following. If B goes to gamma, is a production. Then G. Then add B goes to gamma with a dot there. So far, this is exactly the same thing as the other closure operation. The only thing that differs so far is that A, and this A here is completely and utterly uninteresting for us, or to us, because that A doesn't do anything until that dot has traveled all the way to here. So now I'm going to have to figure out what to put there. Well, I'm going to have a, should we just put a B? Add B to J, where, well, what happens if I just say if I just do that? Well, that could potentially be a problem because what if first of beta is only epsilon, and then I end up with an empty set, and I can't put anything there. Well, what we could do is we could say, well, wait a minute. If beta is empty, then what happens in the next state? Well, then we have a complete item, don't we? Then if this is that not there, then that dot moved over here will be empty. Sorry, will be the reduction, and I expect to see an A on the input. Okay, well, in the case of that, then if I glued that A to the end there, we would get the right A, and if beta wasn't um, epsilon, then that A wouldn't have any effect, but if beta was epsilon, then we would have the A. So what we're going to do is we're just going to spruce that up a little bit by saying compute first of that, which is never epsilon because that is always a terminal. So we can sort of get around that epsilon issue with that. So add that to J if not already there. So that's not too bad. Now, what does the go-to thing look like? Well, the go-to thing looks like exactly the same thing. Nothing has changed. You're just gathering things with dots in front of, whatever it is you're looking for. So the go-to does not change at all. Filling the action table only changes for reductions. Remember, for LR0 items, let's just say A goes to alpha dot, we said for all B in the follow of A, action some state on B is reduced by A goes to alpha for all B in the follow of A. For an LR1, then we'll just say for all B in the set A1 dot 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 AN. We don't need to say that because we already said it, so we get that instead. So in the LR0 case, we quantified over the follow set of over that. In the LR1 case, we just use the reduction locats. Cool. Right. Dangling else again. So does this help on the dangling else? Nope, it doesn't. So the dangling else thing is just basically broken. Now, if you try to do a reasonably small grammar as an LR1 graph, you are going to run into some very large graphs very quickly. So we can definitely say that um, LR1 graphs tend to be large. Now, if I go back and look at this guy here, actually, let's go all the way back to here, and I say, right, um, somewhere, I'm going to have another state where I don't have x goes to dot 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 a. I'm going to have that in. It's going to look very much like this. It's just going to be using this rule instead of that rule. And when you compute that closure, you're going to have the dot there. You're going to add those, and you get these two. But in an SLR, those would just point over here, wouldn't they? And then they would that one would have a sort of a similar one over here, just with the dot traveling on that rule. But these guys would be reused. But if I try to do this sort of same analysis on that, then I would come to the conclusion that well, actually, let's just do it. Let's see. Shall I just copy this? And then clean it up. And we can't do all of it because I don't know what it all looks like. But definitely we have something that looks like x goes to dot 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 a dot 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 comma. I don't know. Shall we call that a little a? No, we shall call it q. And then we have a goes to dot x little a, and b goes to dot y little a. And somewhere we have, well, actually, let's finish that. So that's a goes to x dot a x, and a goes to y dot e goes to y. No, a. I get that. And somewhere else we have that state that looks like this dot there. I don't know what that production look ahead is, but we get that. And x and y. A goes to x dot comma b, and a goes to y dot comma b. So I definitely have something that looks like that, right? And you know, there's some stuff coming off here on an a, and there's some stuff coming off here on an a. So we can see that those two are basically duplicated, right? And those two are basically duplicated as well. Whereas in the SLR, this one would have just pointed here, and this one would have just pointed here. Now, it probably doesn't matter a whole lot here, but what if this had some closure operation that made this a huge graph and this a huge graph? Then that would be duplicated here, and that would be duplicated here. And then this is sort of exponential. It happens a lot, and you get these really, really big graphs. But maybe, let's see, that core is the same as that core. And that is an A and that's a B. So basically that never interferes with that. Couldn't I do the following? And that. So basically what I'm doing is I'm going back towards an SLR. I mean, it's just a coincidence here that this is that is indeed the entire follow set. But I could take these item sets, these states, and just say, right, if I could merge them without creating any problems, then I can save a lot of space, because what I had before, a big thing hanging here and a big thing hanging here, it's just going to be one big thing hanging here, and the same thing over here. So we could merge things if we don't create conflicts. So we can merge states if doing so causes no conflicts, and if the cores of the items are the same. So, in other words, that part is the same as that part, so we can merge them if, by doing so, we don't get into any shift reduce or reduce reduce conflicts. Can I ever merge that with that? No, because they don't have the same cores. Although that core is the same as that core is the same as that core, this is not the same as that. So these will forever remain two different sets, right? Or two different item sets. But that doesn't mean I can't merge these because they have the same cores. So doing so for as much as possible gets us the LALR1 graph. So basically, we could think of it by saying, right, if we have an SLR graph and we get sort of shift reduce conflicts, we can try to do the LR1 graph, which is really really big, and then we can sort of try to merge things together, you know, in an SLR manner, and we only do that if we don't create any conflict. So we start with this big graph and we try to reduce it by simply merging things together that look the same cores, different look aheads, and we don't do it if we cause conflicts. Now, it turns out that you can never merge yourself into a shift reduce conflict. You would already have that, but you can certainly merge yourself into a reduce reduce conflict. And if merging two states would cause a reduce reduce conflict, just don't do it, right? Um, and I will. Maybe we should do this next time. Actually, if I could do that now, we'd be done. Let me just try that. So So is it possible to create a reduce conflict by merging? I think we can probably do that fairly easy, because what if I say A goes to alpha dot reduce on A, and A goes to beta dot, or the other way around, B goes to alpha dot reduce on B. And if I have this one here and I say A goes to alpha dot reduce on B, and A B goes to alpha dot reduce on A. If I merge those, then I get A goes to alpha dot reduce on A or B, and I get B goes to alpha dot reduce on A and B. That is a reduce conflict because AB intersected with AB is not the empty set. So it is possible if I have two sets where there are no problems, look, there are no problems here and there are no problems there. But if I put them together, then I get a whole bunch of problems. So rule is don't do it. So it is possible to create them. So do not merge if it creates problems. Right. So what about shift reduce? So let's look at a state that has a shift reduce. So I don't know. A goes to like that, and let's say there's a little a in that set. So that's the reduced part. Now we need some shifting stuff. So we need that there. Gamma. Then there's some stuff here, and I don't know what it is, and it doesn't matter. That has a shift reduce conflict because there's an A there. You can reduce on that. There's an A there. You can shift on that. But if this is the merged cell, then I can say, well, what on earth happened in the states that I came from? Well, they have the same cores. So these two states both have two items. One that says A goes to alpha dot, and one that says B goes to beta dot A gamma. And again, I don't know what that is. Let's put that one in over here. I don't know what that is, but we know that there's an A goes to alpha dot. And then we can say, where did that A come from? Well, it came from either there or there. I cannot release phase 5 until that would give away the phase 4 answers. So it came from either here or here. Well, if it came from here, then I would have a shift reduce conflict there. If it came from there, I would have a shift reduce conflict there. So shift reduce conflict would already exist in either of the merged states. Right? I've gone 2 minutes over time. I want to say one more thing. Which of the parsing algorithms, LL1, SLR1, and LR1, and LALR1, did we say that? Yeah, LALR1, like that. Which one is the weakest? I'll look at your chat messages. Well, let's just get this over with. So which one is the weakest? Well, this can parse more languages than that. So we saw that SLR can handle left recursion, LL1 cannot, and right recursion wasn't a problem. So obviously, all the left recursive grammars are SLR parsable. Well, They're definitely not LL1 parsable, but some of them are LR1. Now, if I get shift reduce or reduce conflicts in SLR1, then it's probably because I've used a little bit too aggressive approach to reductions, because I used follow sets rather than reduction look aheads. So this can parse more languages than that one. Now, is it true to say that LALR1 can parse more languages than LR1? And you will see in some places, in some books, that they say this is the case. I don't agree, because how do you create the LR1? You merge things for as long as you don't cause problems. So if you're lucky, there are some states that can be merged, and the LA-LR1 graph is smaller than the LR1 graph, and you're happy. But if the rule is that the LA-LR1 graph is created by merging things that don't cause conflicts, then you could argue that the LA-LR1 graph that is the same size as the LR1 graph is a perfectly good LA-LR1 graph if you've done all the merging that you could, even though you couldn't do any. So I would say that this can parse the same languages as that, with potentially a smaller graph. Done. Delete test 3 and bad test if in Espresso. Well, yeah, or make it move it to good test if you implement plus equal on strings. I think it was. Right. Let's just send this to Ben actually before I forget. There we go. Suppose we can stop recording.